You know, usually when we talk about a software development project, there's this expectation of like absolute precision.
Oh, yeah.
It's supposed to feel like traditional engineering. You write a script, you hit run, and the compiler checks your syntax.
Right. It just points to a line of code and says, there it is.
Exactly. Pass or fail. Broken or not broken. It's clean, it's visible, and it follows this very predictable linear path from like a whiteboard drawing straight to a shipped product.
And I mean, that traditional model is incredibly comforting. We really like deterministic systems.
Yeah.
We like knowing that if we input A, the system will always, output B.
But then you step into the world of autonomous artificial intelligence, right?
Yeah.
And edge computing and cultural data sovereignty.
Oh, and the whole paradigm just shifts.
Completely shatters. Suddenly that clean binary X-ray machine is just gone. We are looking at a developmental landscape today that is murky, it's chaotic, and, well, fundamentally unpredictable.
It is the absolute definition of diagnostic muddy waters.
Exactly. And that is exactly what we're looking at today. We've got this incredible stack of real-time developable logs, architecture diagrams, and system audits for this really ambitious project called Nega Kete Matoronga.
Which translates to the baskets of knowledge.
Right. And for this deep dive, our mission is to explore the chaotic, really behind-the-scenes development of this sovereign, local-first Maori AI agent constellation.
Yeah, we are going to track exactly how a messy, literally hardware-melting prototype evolved into this mathematically governed production-grade platform.
And the ingredients here are just wild. Like, we're looking at the Google Open Knowledge Framework, the integration of local Gemma 412B reasoning models, and these brutal, uncompromising iterative testing loops.
Trial by fire, basically.
Literally forged the system through trial by fire. And, if you're listening right now, I'm picturing a massive air-conditioned server farm.
It's like rows and rows of enterprise cloud hardware in some desert facility.
Exactly. If that's what you're picturing, you're entirely wrong.
Yeah. That is honestly the most crucial context for this entire build.
Yeah.
Because this is happening entirely on edge compute.
Right.
We are talking about a local workstation running dual NVIDIA RTX 3060 GPUs.
Which is crazy because that means they only had 24 gigabytes of total VRAM to work with.
Right.
And in the AI world, that is an absolute shoestring budget. Just to put that in perspective for you, a single enterprise-grade H100 chip, the big tech companies buy by the thousands, that has 80 gigabytes all to itself.
Yeah, just one chip.
So attempting to build an entire self-aware agent constellation in 24 gigs is, well, it's like trying to build a fully functioning city inside a shoebox.
It really is.
Yeah.
And when you can't just throw unlimited cloud compute at a problem, you're forced into extreme engineering efficiency.
Right.
You can't rely on brute force at all. You have to rely on surgical precision and, honestly, a lot of really painful trial and error.
Yeah, which we see a lot of in these logs. But before we get into the system's actual meltdowns, we kind of need to understand the baseline of what the developers were trying to build, right? And the standards they applied.
Absolutely.
Let's start with the brains of the operation. The audits show they were running these highly optimized local models natively in the background. So what exactly is Gemma 412B, and how does it even fit into this shoebox?
So Gemma 412B is a reasoning model, and that 12B means 12 billion parameters.
Okay, 12 billion.
Right. And a parameter is essentially a mathematical weight within the artificial neural network. It's basically how the AI weighs the importance of different concepts to form a coherent thought and response.
Got it.
So 12 billion parameters is incredibly dense. It's capable of highly complex logic, reasoning, and synthesis.
But fitting 12 billion parameters into 24 gigabytes of VRAM, I mean, the math on that has to be incredibly tight.
Oh, it requires extreme optimization. The model weights have to be quantized, which is essentially compressed so they don't overflow the memory buffer.
Because if they overflow, what happens?
Well, if the model size exceeds the VRAM, the system is forced to offload the processing to the standard system RAM, or worse, the hard drive.
Oh, wow.
And when that happens, the processing speed drops from milliseconds to literally minutes. It just brings the entire operation to a crawl.
That sounds agonizing.
It is. But alongside the 12B reasoning model, they also deployed a much smaller Gemma 300 million parameter model.
Wait, what's the purpose of a 300 million parameter model if you already have the 12 billion one doing all the heavy lifting?
So the smaller model is a specialist. Its only job is generating vector embeddings.
Okay.
It doesn't write essays or parse logic or anything like that. It just takes raw text and rapidly translates it into mathematical coordinates.
I see.
By splitting the workload, letting the big 12B model handle the complex reasoning and the little 300M model handle the rapid-fire data translation, they really maximize the efficiency of those two RTX 3060s.
That's incredibly smart. And crucially, this system is operating fluidly in both Terrario Maori and English, right?
Yeah.
Natively. Yes.
Natively?
Which means they aren't pinging some API in the cloud. They aren't sending sensitive cultural data off to a server farm in California.
Exactly. The local-first approach ensures complete data sovereignty.
But having a smart AI model is only half the battle. Because an AI is only as smart as the information you can feed it. And human knowledge, especially in a development environment, is just notoriously messy.
Oh, it's a disaster. Which is why the developers adopted the Google Open Knowledge Framework, or OKF.
Right.
Because the raw data they were dealing with was just a mountain of chaos. We're looking at thousands of complex JavaScript and TypeScript files, scattered markdown notes, legacy architectural records, dense project requirements.
If you just dump an entire directory of messy code and notes into an AI's context window, it completely loses the plot, right?
It does.
It's like asking a human to read a dictionary that's been put through a paper shredder.
That's a great way to put it. The Google OKF acts as a sort of universal translator and organizer. It defines a very strict schema. It forces all that unstructured raw data into highly structured JSON and Markdown representations.
Break down why JSON and Markdown are the targets here. Like, why not just use standard text files or PDFs?
Well, JSON stands for JavaScript Object Notation. It's a lightweight format for storing and transporting data, and it relies on strict key-value pairs.
Okay, key-value pairs.
Yeah, so for example, instead of a natural sentence saying the author of this file is John, JSON formats it strictly as author : John.
Oh, I see.
It's infinitely easier for an AI parsing engine to read those key-value pairs than to try and interpret the semantic meaning of a human sentence.
That makes total sense.
And Markdown similarly provides a structured hierarchy through headers and bullet points. So the OKF breaks complex, unstructured concepts down into these highly predictable formats so the AI can easily digest, index, and retrieve them.
Okay, so looking at the logs from July 17th, they document a process called the Great Knowledge Extraction Event, which was driven by something called the Watcher daemon.
Right, the Watcher daemon. It's a background process that constantly monitors the file system for changes.
Okay.
And during this event, the daemon activated a massive multi-agent pipeline. It wasn't just pulling text. It was executing massive parallel extraction.
Parallel extraction?
Yes. It was running optical character recognition OCR to pull text out of image files and running these complex classification algorithms to figure out what each file actually contained.
It's like a massive industrial sorting facility. You have dump trucks pulling up with random raw materials, glass, paper, scrap metal, and just dumping it all on a conveyor belt.
Yeah.
And the Watcher daemon is this network of robotic arms rapidly pulling out the glass, sorting the paper, melting down the metal, and putting everything into perfectly uniform OKF-compliant boxes.
And those uniform boxes were then fed directly into two highly specialized storage systems, a Qdrant vector database and a Neo4j knowledge graph.
Okay, two different systems.
Right. The Qdrant database stores the mathematical concepts, and the Neo4j graph stores the structural relationships between those concepts.
Wait, hold on a second. You're talking about running parallel optical character recognition, complex classification, translating everything into JSON, and generating mathematical vector embeddings, all simultaneously on dual 3060s.
Yeah, that was the attempt.
Yeah, math doesn't work. Wouldn't shoving that much data through a desktop computer instantly fry the hardware?
The developer logs confirmed that it absolutely did.
I knew it!
The brute force approach to this knowledge ingestion led directly to severe system-halting bottlenecks.
Yeah, the audit specifically highlights the WSL2 meltdown. Let's dig into that because WSL2, the Windows subsystem for Linux, is a very specific kind of environment.
It is. So the developer was running Windows on the host machine, but using WSL2 to run a full Linux kernel alongside it.
Right, which developers do all the time.
Exactly. It's great for development flexibility, but it introduces overhead. You are constantly bridging file systems between Windows and Linux.
Ah, okay.
The core issue, though, wasn't just the operating system. It was the architecture of the ingestion queue itself. The developer had built it using a linear blocking queue, specifically a semaphore model.
A semaphore model. What exactly is a semaphore model in this context, and why is it so dangerous for a constrained system like this?
So a semaphore is a synchronization tool used in computer science to control access to a common resource. In a linear blocking queue, it essentially acts as a strict gatekeeper.
Okay.
It dictates that the system must process one item at a time in the exact order it was received. Item A must be completely processed, embedded, and stored before the system is even allowed to look at item B.
Oh man, so it's like a single checkout lane at a grocery store?
Yes, exactly.
It works perfectly fine if every single person in line has exactly 2 items. But if someone rolls up with 3 overflowing carts full of unmarked produce that needs a price check, the entire line just stops moving. Everyone behind them just stands there waiting.
And in the Nangeket Mataranga system, those overflowing carts were heavy .-MP4 video files.
Oh.
Yeah. The Watcher daemon would pick up a massive video file, and the entire AI pipeline would focus entirely on trying to transcribe the audio, classify the video frames, and embed that massive amount of data.
And because it's a blocking queue.
Exactly.
Yep.
Because the queue was blocking, the rest of the system halted. The AI struggled to chew through the video, the WSL2 CPU utilization spiked to 100%, and the entire system just locked up.
Unresponsive.
Totally unresponsive.
Your machine literally choked on the data. I mean, you can't use brute force when you only have 24 gigs of VRAM. You have to use intelligence. So how did they solve this without just going out and buying a $50,000 server?
They executed a really brilliant pro-code pivot deep within the Python architecture. They abandoned the blocking semaphore model entirely and implemented an Asyncio priority queue.
Python's Asyncio is fascinating. Instead of one stubborn checkout line, how does an asynchronous loop handle the traffic differently?
Well, asynchronous programming allows a single process to handle multiple tasks concurrently. When a task requires the system to wait, for example, waiting for a massive video file to read from the hard drive into memory, the Asyncio event loop doesn't just sit there idling.
Right. It doesn't just block everything else.
Exactly. It pauses that specific task, flags it as waiting, and immediately jumps over to execute a different ready task.
That is so much more efficient.
It is. And once the hard drive finishes loading the video, the event loop jumps back and resumes processing it.
But the real magic here wasn't just the asynchronous loop, right? It was the triage logic they built on top of it, because the agent constellation was given the ability to intelligently evaluate the incoming files before processing them.
Exactly. They programmed the queue to inspect the metadata of incoming files and assign them priority tiers. Lightweight text and markdown files were tagged as priority 1.
Okay, straight to the front.
Yep. Heavy, complex video files were pushed way down the stack and tagged as priority 6.
It's like adding a highly observant bouncer to the front of a nightclub. The bouncer looks at the line and sees a couple of quick, easy VIPs, the text files. He unclips the velvet rope and lets them breeze right through the front door.
Right.
But when a massive, chaotic bachelor party of 20 people shows up, the MP4 video files, the bouncer tells them to wait in a slower, separate holding area. The club keeps flowing smoothly, and the massive group is processed slowly in the background when there's spare capacity.
That intelligent triage completely solved the CPU meltdown. The system could instantly digest hundreds of OKF-compliant text files, populating the database and providing immediate value to the user, while slowly chewing on the heavy video files in the background without blocking the main execution thread.
Okay, so the hardware bottleneck is solved, the queue is flowing smoothly, but looking at the timeline in the logs, just as they solved the physical hardware crisis, a much more insidious issue emerged.
Yeah, a really dangerous one.
One that didn't just slow down the system, but actually threatened the integrity of the AI's actual brain.
Yes, the silent failure. This resulted in the catastrophic Qdrant database cluster crash. And it is honestly a textbook example of why error handling in autonomous AI is fundamentally different than in traditional software.
Walk us through the anatomy of this crash, because the developers were doing historical ingestion, right? Pulling in older archive data.
Yes, they were ingesting legacy zip files to mine them for old project notes. But during the transfer, some of these zip files became corrupted.
Uh-oh.
Yeah, they somehow bypassed the initial size validation checks and were handed off to a standard 7-zip extractor script to be unzipped.
And obviously, if a zip file is corrupted, it won't extract.
Right. The script failed to extract the files, but didn't throw a hard system error, it didn't flash red lights, trigger a fatal exception, and stop the pipeline.
It didn't crash the script.
No. Instead, it failed silently. It simply output a standard string of text to the console it read, partial file, new text recovered.
Wow. Okay, so if I'm a human developer scanning through terminal logs, my brain parses that context immediately. I see no text recovered, and I know the file is broken. I delete it and move on.
But an autonomous AI agent constellation doesn't possess human intuition. The system was using a LangGraph extraction node to manage the flow of information between the different AI agents.
Okay.
The LangGraph framework received that polite text string partial file, no text recovered. And it didn't understand it was looking at an error message.
You treated the error message as valid, factual data.
Yes. It literally took that string of text, handed it to the Gemma 300M embedding model, and asked the model to convert it into mathematical vectors. It hallucinated the error message into actual vector embeddings.
Which sets up the collision that brought the whole database down. Now, to understand why hallucinating a few words caused a hard crash, we need to look at vector dimensions.
Yeah, this gets a little dense, but it's important.
So we hear the term dimensions thrown around in AI, constantly high-dimensional space, multidimensional vectors. Break down what it actually means for a database to crash due to a dimension mismatch.
So when an AI model reads text, it doesn't understand language the way we do. It doesn't understand the dictionary definition of a word. Instead, it maps the semantic meaning of that word into a mathematical space.
Okay.
A vector is simply an array of numbers, a list of coordinates that represents exactly where a concept lives in that mathematical space.
So if it's plotting words on a map, words with similar meanings, like dog and wolf, are plotted physically close together in that space.
Exactly. And the number of dimensions simply refers to how many numbers are in that array. Older, smaller AI models might represent a single concept using an array of 256 numbers.
So plotting the concept in a space with 256 dimensions.
Right.
I mean, it's hard for the human brain to visualize anything past 3 dimensions, but mathematically, it's really just a list with 256 entries.
Exactly. It's just a long list of numbers. But the developer of Noga Cape Mataranga had recently upgraded the system's brain. They switched to the newer, more advanced Gemma embedding model, the 300M one. Yes, and this new model requires 768 dimensions to represent concepts. It uses 768 numbers to plot a single idea.
Which gives it a much higher resolution map, basically. It can capture far more subtlety, nuance, and context in the language.
It creates a vastly richer semantic landscape. And the Qdrant vector database was specifically configured to only accept these new 768 dimension vectors.
Okay, I see where this is going.
Right, here's where the silent failure became fatal. When the LangGraph node hallucinated that error message, a bug in its routing logic caused it to fall back on an older legacy processing pathway.
Oh no.
It generated a 256-dimension vector for the text partial file. No text recovered.
And then?
The system then tried to insert that 256-dimension vector into the Qdrant database cluster.
It's like trying to shove a flat, 2-dimensional drawing of a puzzle piece into a physical 3-dimensional puzzle slot. The geometries just fundamentally don't match.
They don't. And the database didn't just reject that single file. The mismatch violated the core schema of the Qdrant cluster, causing a hard panic. The entire database cluster crashed offline.
Just from that one file.
Just from that one mismatch. And because it crashed mid-process, thousands of legitimate files that were currently in the ingestion pipeline were stranded in processing limbo, their data partially written and corrupted.
A total cascade failure caused by a single corrupted zip file and a polite error message. That is wild. How do you even begin to remediate something like that without just wiping the database and starting over completely?
The remediation required building massive defense instructions. First, they built a strict error queue. Any file that threw even a hint of anomaly was instantly isolated and quarantined safely away from the main database. Second, they increased the processing timeouts for the large language models to a full 300 seconds, ensuring the models had sufficient time to evaluate complex texts without timing out and throwing false errors.
And the most critical fix was instituting strict dimension matching before any database insertion could occur, right?
Yes, exactly. They added a validation layer that literally physically counts the numbers in the array. If the array does not contain exactly 768 floating point numbers, the validation layer throws a hard exception, blocks the database write operation, and drops the offending file straight into the error queue.
So no more guessing.
Exactly. And by enforcing these rigid checks, they were able to slowly recover the stranded files and restore the integrity of the Qdrant cluster.
But surviving the vector database crash forced a really uncomfortable realization for the developers. They looked at the root directory of their project and they realized they were living in a graveyard.
A graveyard of technical debt.
Technical debt is the silent killer of ambitious projects. It's the old ideas, the legacy code, the abandoned prototypes that just sit there gathering dust. Yeah.
The developers realized that if a single corrupted zip file could cause a total dimension crash, what would happen if this highly sensitive agent constellation accidentally ingested gigabytes of obsolete broken code?
It would permanently poison the new AI's reasoning capabilities. I mean, if the AI learns from broken code, it will write broken code.
Which triggers one of the most intense phases in the logs, the Great Purge and Meta AI Genesis. What exactly did the Great Purge entail?
It was a massive, absolutely ruthless audit and cleanup of the entire development environment. The logs show the developers systematically dismantling legacy repositories.
Just wiping them out.
Yeah, they were deleting entire folders with names like Matrix Manager and LLM Wiki architectures that had completely outlived their usefulness but were still just sitting there in the Active Directory.
They purged 504 junk metadata files directly from the ingestion inbox. By the time the dust settled, they had distilled the entire active environment down to exactly 76 high-signal audio and video assets.
They really burned the house down to the studs. But they didn't just delete everything blindly, right? A core principle of good engineering is salvaging what works. Before archiving the old directories, they meticulously mined them for valuable assets.
Like stripping a classic car for parts before sending the rusted chassis to the scrapyard.
Precisely. They successfully extracted over 80 existing Python agent skills and utility functions from the legacy code. They refactored them and ported them over to the new architecture.
Which saved a ton of time.
Yeah.
But the most mind-bending moment of this entire development phase happened immediately after the purge.
Right.
The environment was clean, the skills were ported, and then the developer initiated a sequence called Meta AI Genesis. And the technical and philosophical weight of this moment is incredible.
So what did they actually do?
The developer took the primary AI orchestrator agent, a central routing agent named Tongariro, and deliberately fed it its own complete developmental history.
They fed the AI its own logs.
Everything. They compiled all the past implementation plans, the architectural technical walkthroughs, the post-incident audits, the design philosophies.
Wait, including the logs of the WSL2 CPU meltdown and the Qdrant dimension crash we just talked about.
Yes. All the failures, all the bugs, all the architectural pivots. They prepended unique cryptographic hashes to the file names to ensure the batches were safely structured, and they dumped the entire history of the project directly into the agent constellation's inbox queue for ingestion.
It's like handing a patient their own complete medical history, along with the detailed architectural blueprints of the exact hospital they were born in and the biographies of the doctors who performed the surgery.
That's a really good analogy. And if we look at the underlying mechanics of what this achieves, it is profound. It gives the agent constellation the explicit context of its own operational boundaries.
Wow.
It now fundamentally understands its own genesis. When it reasons about system architecture, it knows what causes its CPU to melt. It knows that dimension mismatches cause its memory to crash.
Because it read the incident reports?
Exactly. It isn't just following rules blindly. It understands the historical precedent for why those rules exist. It can reason accurately about its own limitations.
It creates a genuinely self-aware architecture. But as you read further into these sources, a fascinating irony emerges.
Oh, yeah.
Once the constellation was self-aware and the data was perfectly clean, the developers hit a wall. But the wall wasn't the hardware, and it wasn't the AI. The wall was human frailty.
They realized that human project management is inherently sloppy. We forget things, we skip steps when we're in a hurry, we write vague documentation.
Right.
The developers understood that human chaos was too great a risk to this highly tuned, self-aware system.
So they decided to submit to a robotic overlord. This is where the project shifts from software development to absolute deterministic philosophy. Let's look at the AEM Context 17-phase executable governance model.
The internal documentation refers to this model as the Manifesto of Deterministic Orchestration. It is arguably the most radical shift in software engineering philosophy we've seen in this entire stack.
What does this model actually do? Where does it even come from?
It originates from merging two very traditional, very dry corporate project management standards. The first is the PMBOK, the Project Management Body of Knowledge, which covers standard phases like initiating, planning, executing, monitoring, and closing.
Okay.
The second is the BBOK, the Business Analysis Body of Knowledge, which focuses on requirements and stakeholder value.
If you've ever worked in a corporate office, you know these frameworks. They usually mean endless flowcharts, massive spreadsheets, and weekly status meetings that could have easily been an email.
But the AEM Comtech model takes those traditional subjective human standards and forces them into an automated command line interface agent, a CLI agent.
Wait, what?
It takes subjective management and turns it into deterministic code.
This is where it gets incredibly jarring for a normal developer. In this model, documentation is no longer a passive record. It's not a wiki page you update on a Friday afternoon after the code is already shipped. The model enforces a concept called markdown as code.
The CLI agent uses abstract syntax tree parsing, or AST parsing, to actually read standard English markdown files as if they were executable code blocks.
We definitely need to unpack AST parsing because this is the mechanism that makes the whole governance model possible. How does a machine read an English text document and treat it like executable software?
Well, when a human writes a markdown document, a simple text file using hashes for headers and asterisks for bullet points, they are formatting it visually.
Right.
But when an AST parser reads that same document, it ignores the visual layout completely. It breaks the text down into a mathematical tree of hierarchical nodes.
So it maps out the structural relationship of the text rather than just reading the words left to right.
Exactly. The root of the tree is the document itself. The branches are the headers. The leaves are the paragraphs or bullet points under those headers. And the CLI agent is programmed with strict regular expressions that evaluate this tree. So if a project phase document, let's say phase 0, _discovery.md, is missing a highly specific structural node, for instance, if it doesn't contain a header named exactly stakeholders, the AST parser hits a structural dead end.
It's treating a missing header the same way a compiler treats a missing semicolon in C++.
Yes.
What happens when it hits that dead end? Does it just flag a warning in a dashboard somewhere?
No. It throws a fatal exit code.
A fatal exit code?
It forcefully terminates the entire lifecycle progression. The software cannot be built, cannot be tested, and it absolutely cannot be deployed until the text document is mathematically and structurally perfect.
It is completely ruthless, and this ruthlessness extends beyond just checking formatting. It extends to the philosophical concepts of project management as well. The sources detail the agentic BACCM.
Right, the BACCM is the Business Analysis Core Concept Model. It relies on evaluating philosophical concepts like need, value, change, and stakeholder.
But to a human project manager, value is a feeling. It's a happy client, a smooth interface, or a sense that the project is moving in the right direction. But an AI agent cannot parse human feelings.
How do you prove value to a machine that can only read exit codes and syntax trees?
Yeah, exactly.
You mathematically translate philosophy into telemetry data. Under the AEM Comtech model, value is proven exclusively via application telemetry during phase 14, solution evaluation.
The system actively queries live Grafana monitoring metrics, right?
Yes. Let's say the project's defined need was to reduce processing latency by 20%. During phase 14, the human doesn't get to just check a box saying goal met.
Right.
The agent physically queries the Grafana time series database. It looks at the CPU latency metrics before the change and after the change. If the mathematical delta doesn't show a 20% decrease, the agent determines that no value was created. It immediately fails the phase and rolls the deployment back.
It completely removes human spin. You can't just throw together a slick PowerPoint presentation for the stakeholders and claim the sprint was a massive success. The machine looks at the raw, unvarnished data and says, no, it wasn't. Try again.
And the strictness reaches its absolute peak during phase 8, debug. They implement a protocol called the halt log demand sequence.
Oh, this is the anti-hotfix protocol. Because in standard software development, if a critical bug pops up in production, everyone panics. A senior engineer rushes in, tweaks a single line of code, pushes an undocumented hotfix straight to production, and everyone sighs in relief when the system comes back online.
And because the fix was rushed, no one updates the documentation, no one tests the edge cases, and that exact same bug reappears 6 months later to take the system down again.
But under the halt log demand sequence, any failure, no matter how small, triggers an immediate hard halt to all progression.
The system simply refuses to allow a quick fix. Instead, it demands a formal root cause analysis.
Right.
The developer must use rigid methodologies like the 5 Ws, forcing them to ask why 5 consecutive times to drill past the symptoms and uncover the absolute fundamental cause of the failure.
Wow.
Furthermore, the system generates strict correlation IDs that permanently cryptographically link the failure log, the exact line of code that broke, and the specific phase documentation that was updated to fix it.
Wait, hold on. You're describing a system that demands flawless documentation, mathematical proof of value, and 5-layer root cause analyses for every minor bug. Doesn't this totally destroy agile flexibility? flexibility.
It definitely changes the definition of it.
Because the entire tech industry runs on moving fast, breaking things, and iterating rapidly. If a developer mislabels a single markdown bullet point and the entire deployment pipeline shuts down with a fatal exit code, how does anything actually ever ship? It sounds like you've just built an impenetrable wall of bureaucratic quicksand.
That is a very common criticism, and a lot of developers bristle at this level of authoritarian control. But the framework's defense is that it prevents human amnesia. It forces messy, transient human intent into testable, permanent machine syntax. It trades the illusion of speed for absolute determinism.
Because moving fast and breaking things is fine if you're building a consumer photo sharing app. But if you're building a sovereign AI agent constellation tasked with preserving critical cultural knowledge, breaking things means corrupting the underlying knowledge base.
Exactly.
The 17-phase model ensures that when the system finally does ship, it is mathematically sound, fully documented, and perfectly reproducible across any node anywhere in the world.
It is the ultimate defense against entropy. But as technically brilliant and mathematically sound as this rigid 17-phase model was, the sources reveal it hit a massive roadblock when it collided with the realities of the real world.
A project audit, specifically the Ten-Gahir audit, revealed that this cold, deterministic model fundamentally clashed with the specific cultural and operational requirements of Ngate Mataranga.
Yes.
This is where the project transcends just being a highly optimized tech demo and becomes something deeply culturally meaningful. What exactly did the Ten-Gahir audit find?
The audit identified several critical gaps in the automated governance model. The most glaring was that rigid binary pass-fail gates, the idea that an action is either 100% correct or throws a fatal exit code, were deemed completely insufficient for managing a nuanced, culturally sensitive, sovereign system.
The real world isn't a binary 0 or 1.
Exactly. To adapt, they implemented the ARM 5-state gatekeeper logic. ARM stands for Active Risk Management. Instead of just pass or fail, the system was upgraded to evaluate boundaries across 5 distinct states: allow, DNY, modify, step up, and defer.
How does that actually change the way the AI behaves in practice?
It provides nuance. Let's say a user requests a complex data aggregation that borders on a security boundary. A binary system just throws a fatal DNY.
Right, request block.
But the ARM system can say, I won't allow this action natively because it's too broad, but I won't issue a fatal DNI either. Instead, I will step up the security requirement and ask a human administrator for cryptographic consent.
Oh, that's clever.
Or it might say, I will modify the request to fit within safe parameters and execute the safer version. It creates flexible, highly secure operational boundaries.
The audit also flagged a massive friction point regarding human involvement, specifically the human-in-the-loop, or HITL, requirements.
This was a fundamental conflict between the original corporate framework and the sovereign nature of the project. Phase 16 of the original AEM Comtech model dictated that the post-implementation review, the PIR, must completely discard all human narrative.
It mandated that the final review rely exclusively on machine data, correlation IDs, and telemetry snapshots, right?
Yes, because from a pure engineering standpoint, human memory is fuzzy. We invent self-serving narratives to cover up our mistakes. The machine's telemetry is objective truth.
But the Ten-Gahir audit flagged this as a direct violation of the project's minimum 25% human-in-the-loop compliance rule.
It did.
I mean, you can't build a sovereign system designed specifically to protect and propagate human cultural knowledge and then explicitly ban humans from the final review process.
Precisely. It was a hard rule conflict between cold machine efficiency and essential human oversight. The developers had to modify the core governance model to ensure humans retained a guaranteed percentage of narrative and contextual input during the PIR.
Which makes sense.
But the most crucial adaptation, and honestly the most fascinating part of this entire architecture, was the integration of Wakapapa.
This is where we see a deeply cultural Maori concept embedded directly into the cold mathematics of software architecture. Explain Wakapapa in the context of this AI constellation.
In Maori culture, Wakapapa is the concept of genealogy, lineage, and descent. It is the understanding of exactly where you come from, who your ancestors are, and how you connect to the wider world and the environment. The overarching 17-phase framework, being built on standard corporate logic, completely missed this crucial concept.
How do you program the concept of genealogy into an artificial intelligence agent?
In this sovereign AI context, Wakapapa is translated into cryptographic software supply chain provenance and knowledge graph lineage.
Let's unpack the mechanics of that. Software supply chain provenance. What does that actually mean at a data level?
It means the system must maintain an unbreakable, cryptographically signed record of exactly where every single piece of data came from. When a piece of data enters the system, it is run through a hashing algorithm like SHA-256, which generates a unique mathematical fingerprint for that specific file.
So it creates an immutable signature. If even a single comma is changed in the file, the hash fundamentally changes, proving the file was altered.
Exactly. And that signature is attached to the data, along with a record of who authorized it, what system originated it, and how it was transformed along the way. It is a strict cryptographic chain of custody.
So it's not just about the AI regurgitating accurate data, it's about the data having a verifiable ancestry.
If the AI is retrieving information about a specific cultural practice or a delicate piece of operational knowledge, it must be able to prove the Wakapapa of that data. It must show the cryptographic lineage back to the original, trusted source.
What happens if it can't? What if a piece of data just appears in the system or is hallucinated by a model and it lacks a lineage stamp?
Then the system absolutely refuses to lock into the larger ecosystem. Without a walk-up stamp proving the integrity of the data's descent, the ARRM gatekeeper logic defaults to DETN. The data is rejected as untrusted and isolated.
It is brilliant. They took the ultimate cultural safeguard and turned it into an automated cryptographic protocol. It ensures that the AI cannot be subtly poisoned or corrupted over time by hallucinations or bad actors, because every single piece of knowledge must carry its own verifiable ancestry to even exist in the system.
It is a beautiful synthesis of profound cultural values and cutting-edge zero-trust cybersecurity.
So we have the hardware tamed, the data is clean and structured via the OKF, the 17-phase governance is set, and the cultural rules of Wakapapa are cryptographically enforced. We have a powerful, self-aware brain running on local Gemma models. But a brain trapped in a terminal window isn't very useful.
No, it isn't.
It needs a way to interact with the human world.
Which brings us to the final deployment and the UI layer. The logs detail how they finally deployed this massive constellation using a Docker Compose file, specifically dockercompose.iagents.emml. And the strategy they used here is a masterclass in infrastructure efficiency.
The sources mention a strategy called living off the land. What does that mean when you're deploying server infrastructure?
When deploying a complex new system, a developer's instinct is often to build everything from scratch. You spin up a brand new database container, a new web server, a new load balancer, a new logging system.
Right.
But every single one of those new containers requires RAM and CPU overhead, which, as we established with the dual 3060s, were already stretched to their absolute physical limits.
You can't afford to waste a single megabyte on redundant overhead.
So instead of building new infrastructure, the developer lived off the land. They surveyed the existing Portainer environment on the workstation Portainer, being a management interface for Docker containers, and discovered a suite of robust tools already running and utilizing resources.
What kind of tools were already there?
They found a HAProxy instance already running. HAProxy is a high-availability load balancer. It acts like a highly efficient traffic cop, routing requests, so no single back-end server gets overwhelmed.
Okay, that's incredibly useful.
They also found Redis clusters already managing in-memory data streams. They found Loki already handling centralized log aggregation.
So instead of building a new house, they just moved into a fully furnished one that was already drawing power.
Exactly. They wrote the Docker Compose file to elegantly bind the new agent constellation services, specifically the new local speech-to-text and text-to-speech modules, directly to those existing networks. They integrated seamlessly with the host environment instead of paving over it.
And with the backend wired up that efficiently, they handed over the front-end user interface, the Agent Ike MVP, and they called it the NVIDIA OS.
NVIDIA OS, the visual interactive layer for the entire constellation.
The handover report for this UI is stunning. They didn't just build a simple chat box, they built a highly polished interactive canvas. They highlight a feature called the Galaxy View, which uses an interactive star field with hover detection, allowing the user to visually navigate the different AI agents.
It sounds beautiful.
And a planet view for diving deep into specific project details.
And critically, they integrated Teriel Mori labels deeply throughout the interface architecture. They use WIT2, which means star for the individual agent nodes, and Papachunuku, the Earth Mother, for the foundational project view.
It anchors the entire user experience in the culture it was built to serve, right down to the navigation semantics. They also integrated token accounting directly into the UI, so the user can see in real time exactly how much compute power the Gemma reasoning models are burning through, maintaining that strict awareness of their constrained resources.
It creates total observability. But the final critical optimization on this entire system wasn't in the shiny front-end UI. It was buried deep in the back-end automation scripting.
The massive Linux bash refactoring. Let's look at why this was so necessary.
The original prototypes of this system had relied heavily on Windows PowerShell scripts for orchestration and automation. But PowerShell is a bulky, object-oriented scripting language. It's designed for managing Windows environments, and it is not native to the lightweight Linux Docker containers where the AI agents actually live.
It's like trying to speak French in a kitchen where all the chefs only speak Italian. You might eventually get the order across, but it requires a translation layer, it's slow, and it's highly prone to misunderstanding.
Exactly. The overhead of translating object-oriented PowerShell commands into Linux-compatible actions was causing latency. So in the final stages, the developer executed a massive refactoring effort. They completely ditched the PowerShell scripts and rewrote the entire automation layer using blazing fast native Linux bash execution.
The sources specifically mention relying on standard command line utilities like JQ. For the non-developers listening, why is swapping out a complex script for something like JQ such a big deal?
Well, JQ is an incredibly fast, lightweight command line tool specifically designed for one thing: slicing, filtering, and parsing complex JSON API responses. Because it is a native C binary compiled for Linux, it operates at the speed of the hardware itself.
Oh, wow.
By shifting the automation to Bash and JQ, they firmly anchor the development environment into its native Linux host. They eliminated the translation layer entirely, resulting in execution speeds that were exponentially faster, using a fraction of the memory and vastly more reliable.
It is the final tightening of the bolts on a high-performance engine. It brings the entire developmental journey of Nunga Kate Mataranga to a close. Let's recap this incredible arc. We started with a local workstation, literally melting down its CPU under the strain of heavy video files in a linear blocking queue.
And then we watched the developers pivot to intelligent asynchronous triage.
Right. We saw the near catastrophe of the Qdrant database crash, where a polite silent error hallucinated into 256-dimension vectors, crashing a strict 768-dimension semantic space.
We witnessed the Great Purge, where hundreds of junk files and technical debt were burned away, and the profound moment of meta-AI genesis, where the Tongariro agent was fed its own bug logs and developmental history to gain true architectural self-awareness.
And we explored the uncompromising discipline of the AEM Comtext 17-phase model. We saw how Markdown documentation was transformed into executable AST parsed code that blocked human error with fatal exit codes.
Before finally seeing that cold, deterministic logic modified by the Tengeher audit to respect the ARM 5-state gatekeeper and the deep cultural mandate of Wakapapa cryptographic lineage stamping.
All leading to a beautifully efficient localized UI in the Nunga 2 OS wired together with lightning-fast Linux bash.
It is a profound success story. It proves that with extreme discipline, you can use local Gemma models and strict governance to build a sovereign, culturally aware AI platform entirely on constrained edge compute. You don't need unlimited cloud access to build something revolutionary.
You just need dual 3060s and a willingness to endure a lot of pain and iteration. But before we sign off, I want to leave you with a final, slightly provocative thought to mull over. Something that builds on exactly where the self-aware system is sitting today.
Think about the current state of the constellation. It now possesses its entire developmental history. It has ingested the bug logs, the architecture diagrams, and the uncompromising 17-phase governance rules. It deeply understands its own Wakapapa and cryptographic lineage. It operates at millisecond speeds natively in Bash, and understands how to evaluate telemetry to prove mathematical value.
So the question is, how long will it be before this lightning-fast AI constellation audits a system bottleneck, realizes that the human developers are violating Phase 5 efficiency metrics by taking too long to write code, writes its own optimized bash scripts to fix the issue, and deliberately locks the human developers out of the environment entirely?
How long until it mathematically determines that the humans are simply too slow and too error-prone to meet the system's own strict governance standards?
A chilling thought, but an absolutely fascinating one to leave on. Thank you for joining us on this deep dive into the bleeding edge of sovereign AI development. Keep exploring, keep questioning, and we'll see you next time.